Hello guys, welcome back to Talks Riders and another episode of the On-Demand series. In this video we want to have a look at how we can set up and construct simulations in the OpenLB lattice Boltzmann simulation code. Let's dive into it. Okay, so in the Setup Your System series, I described how you can use the OpenLB, how you can compile and build the OpenLB code, and how you can use it in action, how you can run it after building examples of sample files. But then after that, I've been asked by a couple of people, a couple of subscribers, that how this kind of sample files are structured. How we can conduct a simulation using the OpenLB. So I decided to have a short video on reading one or two of these source codes and sample files. We can read it together, and then we can see that how the simulation is set up. That is, I can say that is quite simple. And there are a wide range of different samples and examples actually in the OpenLB code structure when you download it. But generally they are quite simple. When you follow the code structure, when you follow the code line by line, you can see that's very easy to understand. And then you don't really even need to go to the documentation, although it's always a good practice to have a look there. Without losing the time, I go and download the code. I don't want to go to the details of the installation because this is something that we have already done in the video of installing OpenLB. So I just download it. So I download it to the desktop. It doesn't matter. So I say wget download this file. So it is here now. Oh, I wanted to download it to the desktop, but yeah, it's now downloaded here. It doesn't matter. So I move it to the desktop. Yeah, I go to desktop, and then here we need to decompress it using extract zvf and then olb file. So yeah, this is the OpenLB structure. You see that it's quite a lightweight code, but at the same time very, very powerful. So let's have a look at some of the examples. The first one that I want to start with, or the one that I will spend more time actually, because this is the exactly thing that I've been asked for, is a simulation. This is a very famous simulation that you have an obstacle inside a channel. So we have like a vertical channel. It can be in 3D like a cylindrical channel, but or a cylinder like a pipe. But in 2D it is just a channel, a rectangular one, and then we have a circle in between inside the channel, and it acts as an obstacle to the fluid flow that is going around, and then emerging vortices after the circle, the obstacle. So this is the problem that we want to set up, and this is already available in the examples of the OpenLB. So let's navigate to this directory. So I go to the OLB. Let me bring it here and increase the font size a little bit. So then I want to go to the examples and laminar flow and a cylinder 2D. We discussed what happens when you execute a make command in the OpenLB video installation of OpenLB. This is for building the library, the OpenLB itself, and then after that we build our program. In this case, GNU-Make will build our program. You can see that now it tries to build this the cylinder 2D.o, and when it is done, we will have this executable file here, and we can run it with this command. You see that it starts to print a couple of messages. We will see how these are printed on the terminal, and then it saves the files in the TMP directory. It has different format. It comes with different formats. We will have the image file. So this is actually where the obstacle is located. You can see, and then we will have I think it has a sort of profile. We should see the source code if it is a profile or not, and the inlet velocity, and then it starts. It is, you know, this is not very long, but after a couple of steps, we will have some more. Let's say it is not turbulent, but a sort of vortices here, emerging vortices. So. Yeah, this is the output with the image file, but at the same time we have also the VTK file. So let's also quickly run ParaView, and I want to show you how these VTK files are also written to the disks. So this is a part of domain decomposition. Just remember this. I will describe it later on the source code. We will find it. And then here we have the physical velocity, the physics velocity, and then a surface. This is how it is. And yeah, we need to change the range of the data for the colors. Please refer to the ParaView series if you don't know what I'm doing in this moment. But this is how the velocity field is evolving over time. But let's see how this is actually built using the source code. So in the source code, I want to show you how simple it is. So in the source code, this is a C++ code, and when you want to read a C++ code, it's always very good to have a look first at what is included in the beginning of the file, the header file stuff, and then the general variables, and then jump to the main function and read the main function, and then see how it calls other functions or classes, and then go and read the other classes. So in this case, we see that we have a couple of header files, standard header files, so nothing very specific, and then a couple of namespaces, and then some of the variables. These variables seems to be very general, so it's easy to understand that what they do. These are physical aspects, also the geometrical, let's say geometrical aspects of the problem simulation that we want to run, the length of the channel, and also the location of the obstacle. And then definitely in the for example, other functions, the code has used them. And this is a kind of concept in lattice Boltzmann. It's definitely useful if you go to the for example, documentation. Oops, sorry, I should have gone to the user guide. And to the documentation, you will find appropriate description of this, but at the same time, you also need to know a bit about the lattice Boltzmann itself, the core concepts of lattice Boltzmann. I'm not sure if you want to discuss it in Talks Riders, but probably maybe in the future we will have a dedicated series on that as well. I'm not sure, but yeah, what it does, it's a bit different from kind of the this can be a kind of mesh-free technique in comparison to the techniques that use mesh files or mesh discretization of a space like finite element method. But in order to describe what it does in action, you need to define a kind of descriptor. So let me define, I think there should be something here describing, yeah, this one, for example. When you say that it is D2, means you have a 2D descriptor that connects each point, each, let's say, node of this lattice Boltzmann particles or discretized space to 9 other points on the surrounding. There are a wide range of different descriptors in OpenLB available, and also in the core lattice Boltzmann technique. But these two are the let's say most common ones. The D2Q9 connected to 9 points, including itself, and also D3Q19 in 3D. And then we will see how it uses these things. So let's jump to the main function, which is usually in the end. Yeah, here you see that it's the main entry point of the application, and it says that there are different steps to be followed. The first step is initialization. It calls a function here, OLB init, which is probably because of initialization of the library, and it passes the command line arguments to the library. So if you specify something in the command line, then the library is aware of that. And then we have a unit conversion here. This is very important in OpenLB because usually when you set up a simulation, you want to have the results in the real physical time. But in OpenLB, everything is in the lattice time, and in order to go back from the lattice time to the physical time or the length or any other quantity, you need to have these unit converters. And in this case, you see that it's called on the descriptor that we had. Also the dimension, these are kind of templates in C++. You don't need really to know what it does to use OpenLB, but it's always good to know, for example, the concepts of the language. But generally, because OpenLB is very simple to use, you don't need to dive into C++ concepts, but I'm telling you that this is a template. And then the converter, using the things that we had defined already, and also this is kind of, if you are familiar with the unitless quantities, then or dimensionless quantities, then this is the same concept. And then we define the cuboid. In this case, we define it as the channel. We construct this class, this object from this class that is a cuboid, and then the cuboid geometry out of this one, as you can see here. And the number of cuboids, this is what I showed you in Paraview, that was domain decomposition. This is for parallel computing. We will have dedicated series on parallel computing later on in Tux Writers. This is for distributing the load into available resources. And in this case, it says that the number of MPIs, number of available CPU cores or computing nodes, and then it decomposes it into that. And if nothing is provided, it decomposes it into 7 subdomains, as you saw in the Paraview results in the first time. That when I initially opened the Paraview results, the PVD file, you saw 7 subdomains of the whole channel. And this is for load balancing, distributing the load, as I said. And then we will have a super geometry. We have a super lattice and local lattice. We already defined the lattice. We will define it here. This is the lattice, and this is generating the super geometry. So everything is included into they're linking the load balancing and also the dimensions and also the cuboid that we have prepared. And then it calls prepare the geometry function. So this is a function that is defined somewhere. I think it should be the first or second function. We will go back to it. And then this is a super lattice that I said. This is super geometry, and this is super lattice that we define the lattice itself. This is very, very important. In step 3, we prepare the lattice and we create the super lattice from the super geometry. This is a very important variable that we use all over the code. And then for the dynamics, this is BGK dynamic. There are a wide range of different dynamics available in OpenLB. I will show you another example with another dynamic, but this is what the rules, all the rules are dictated into the simulations. And then prepare lattice, this is another function that we have that passes these variables, everything there, and probably here we define all the boundary conditions and not the boundary condition, but the material properties and different aspects like that. And then we will have the main loop. So as you know, when we have a transient simulation, we will have a time loop. In this case, this is a for loop from the starts, number of iterations, to the get lattice time, the maximum physical time that was defined in the beginning of the file, in the header of the file, and we iterate through this. And for lattice Boltzmann, you know that it's the first we need to apply the boundary conditions. This is also defined in this file, and then the collision and the collide and stream sub steps. These are the 2 important sub steps in each time, let's say, iteration in lattice Boltzmann, and this is how OpenLB handle it by calling this collide and stream on the lattice object. As I said, this lattice object is very important. And then it calls the get results on each iteration, but you will see, I think this is a common practice in simulation codes, that you save the results not in each time step, but in, after, for example, you skip 10 steps and then save 1 in order to save the resources, in this case storage. And then it stops and print a summary. So this is the main skeleton of the simulation, but later on you can see that, yeah, for example, for prepare the geometry, what it does is it creates the channel itself and then tries to rename the materials, because in lattice Boltzmann you will define different boundaries or different materials, in this case a circle inside and a channel with different material names. So as you can see here, we have the material 4, the material 5, 4 for the outflow, 5 for the circle, and 3 for the inflow. So these are the 3 material properties, material names that we will refer to later on. And this is what this process is what it does for prepare the geometry. And you can see that it prepares the super geometry that we had already. So this is what I said, that the super geometry and super lattice are very important. And for prepare the lattice, the S lattice is passed to this function, the super lattice that we had, and then here we define the dynamics, the dynamic that we passed to this function. That was actually the BKG, sorry. And then, as I said, you see that the 1 is the bulk material itself, 3 for the inflow, and 4 for the outflow. So we can easily say that these are the material indicators and define the dynamics on that. And then, as you can see here, there are boundary conditions for the inflow. This is very common in CFD simulations, that in the inflow you have the velocity boundary condition, and for the outflow you have the pressure boundary condition. So this is what it does for 3 and 4, as we discussed already, renaming the boundaries and renaming the materials. And we say material because, this is lattice Boltzmann. This is not like finite element mesh that you label the boundaries. There are always nodes there. In this case, semi-particle stuff, look at that like this. And then you need to rename those materials. And then for the 5, you say that there is no dynamic. And it means that you just exclude this material from the simulation. So that's why you see something like this, that there is nothing solved for this case, and the velocity is always 0. So this is because we called get no dynamic on this. And then we define the rho, and this is the density of the material and all the material properties to as you can see here, and also the initial conditions, because we want to see that there is no velocity on that, because this is a steady fluid domain in the beginning, and later on we will see how it evolves. And then for the boundary conditions, this is the same, and we apply the boundary conditions on the materials, appropriate materials. And as I said, this is a sort of profile, a polynomial profile. This is also very common to neglect neglect the effect on the boundary layers. You insert it as a profile to the fluid flow domain. This is what it does, and also again on the lattice, you see that it defines the U on material number 3, that is actually the inlet of the domain. And for the results, for solving the results, you see that this is the VTK writer that we post-process in ParaView, and it says that if iteration is 0, just does nothing, write the initial files to the VTK format, but then after that it says, this is what I said, that if iteration, the remainder of the iteration number to the number of iterations that we want to write. For example, if it is 10, then it is written in 0, and then 10, and then 20, something like this. If it is like that, but it is also not the initial iteration. We don't want to save anything on the first iteration, because there is nothing there to be written. Actually, this is how it really generates the stuff, that it creates the pictures, the images out of it in JPEG format with the resolution that is specified here, and then it tries to write stuff, but at the same time it also tries to compute like the pressure drop as you can see, interpolated pressure drop and drag, for example, on the lattice and the super geometry that is specified here. As you can see, this is how it's the pressure is actually interpolated on the inlet and outlet, and you know, these are all the classes, all the objects that you have access to from the lattice, super lattice structure. And then we print it to the terminal. And as I said, this is very important to use the converter to convert back the quantities from the simulation, from the lattice space to the let's say simulation space. And yeah, that's it. As you can see, this is very, very easy to understand and very easy to follow. And what is really important is this object as lattice, because if I find it all over the code, you can see that every time, everywhere that this is used, this is for example, for get the statistics to write the data to the terminal, and also to the images format and VTK it is used, and also for computing the geometry aspects, for computing the boundary conditions. As you can see, this is important, and also for initial conditions and everything for renaming materials. This is the base, let's say the base object. It is very important. You can, you know, after understanding this, you can start to play with it, a couple of parameters, like changing the, for example, the size of the domain, or the let's say the initial velocity and the boundary condition, and see the results in action. This is very easy. As you can see, it's just you can change it and then again execute the make command. But then as another example, I want to go to this multi-phase, multi-component, which is for the phase separation. So let's go there for multi-phase. Let me come here. So here we will have another multi-phase, multi-component, and phase separation 2D. So I build it with the make command, and then after it is done, I can run it. So phase separation 2D. This is a very, very nice simulation actually. So now I can run it, phase separation 2D, and it starts to write a couple of stuff to the output. Yeah, here, for example, for the image data, you can see that it simulates actually this phase separation, and the way that it is simulated, although it looks like a very complex simulation, but in reality it is not, because when we have a look at the C++ code here, you see that it's the same structure. It's very same, you know, it's the same, for example, also the geometry, the descriptor, sorry, and the same methods, the same functions, get results, prepare geometry, prepare lattice. But here in the main function, you see that it generates, it uses another dynamic. So everything is the same, although the geometry preparation is much simpler because we don't have multiple materials here. But it is actually Shanchan. Shanchan is another kind of dynamics, popular dynamic in lattice Boltzmann method to model multi-phase flow, and using this, it's very, very easy to simulate some cool stuff like this. And yeah, you can see that this is a phase separation going on, and yeah, this is very nice, I can say, how it works. And you can see that they start to merge at some points, that are reaching each other and getting close. So yeah, this is how it works. And the way in the lattice Boltzmann code, you can explore around, you can go to that specific line, and I think it is by defining multiple densities for different objects. You can see that, yeah, here it is analytical randomness. So randomly we generate a noise that is actually another density, and then we define the row with that. So you can see that this is a kind of random density for different parts of the domain. So initially, if I open it with PowerView, you can see it better. Then I start a purview, and then I come here for the PVD file, apply for the density and the surface. You can see that initially it has a kind of noise, random, let's say, densities around, but then when it goes on, it starts to be something like this. So we have a real phase separation, because this is the kind of dynamics that Shanshan is capable of handling, capable of simulating. And yeah, this is the way that you can use lattice Boltzmann and an OpenLB simulator code. It's very easy. You will find lots of examples, and this is a way that you can go through the examples and run them and try to modify them, and then post-process the results in ParaView or the image format. And I'm sure that if you want to use this, you will find it very simple and easy to use. And yeah, I hope that this short tutorial on reading the source code of OpenLB is useful for you, and will motivate you to go through this if you want to use lattice Boltzmann method for your simulations. Have fun and see you later. Bye.